Okay, so we will today do another algorithm. Okay. This is the Grover's algorithm. This is not an algorithm that gives you, well, at least tentatively gives you exponential advantage. It will only give something that is called a square root advantage. But happens to be, first of all, it's an advantage, even if it's a square root. Secondly, it's a very nice one, very instructive. Uses quantum parallelism in an interesting. So it was discovered by law of Grover, 1996. So, just as in the case of the previous algorithm, we will begin with a story. So, and the story is that Alice is in love, with a boy whose name she doesn't know. So, well, for people in quantum information, this question is like asking, because we will finally call him Bob, okay? So, so this is like asking, "Tumhara naam kya hai, Basanti?" But although we will call him Bob, but it could have been Charu, Devu, or whatever. But she knows his phone number. Well, don't ask me how. Well, somehow. But then, of course, she can just call up that number and ask his name. But then, when in love, you do strange things, and so she does not want to do that. She wants to know the name from some other sources. So, she, of course, will have to search some directory. So she gets hold of a directory, which has, and unfortunately, as you know, that in directories, well, unfortunately for her, but fortunately for us, for the other people, that the names in a directory, the numbers don't come as arranged in, not in numbers, it is arranged in terms of the names. So it is completely random, yes? So she'll have to, there are n names in that register, so there is a register. So there is a classical register. And this register has some n entry, this n is very large. And to find out, she has to look at one after the other. So this needs, on an average, n by 2 queries. Query means you open the book and look at number 1, then number 2, and so on. You will go on checking all the names and the numbers, yes. That's a query.
So why n by 2?
On an average.
You can try to find it. It's, I think I did this calculation carefully, and it is, I mean, it's around n by 2 is It has something else with it. But the highest power is n and the factor is half. That is fine, but there is something else with it. So in the quantum case, we will do something. We will first of all formulate the problem in the quantum case, and we will try to reduce this n by 2. Yes, this is the problem. So we will go to the quantum formulation. So to set up a problem, we again consider a black box, just like in the previous problem. We consider a so-called black box that implements the unitary U given by the following is U on Y is Y if sum A of Y, we will tell you what is A, is 0, and it's minus Y if 1. So these Y's, Y's are the names of the person having phone connections. So this vector Y is the encoding of the Yth name in the quantum situation. I mean, the Yth name in the sense if you have already encoded the names into binary formulation, or you can say encoding of the name Y. Finally, we will make all these digits by bits, many bits. In the quantum situation. Okay. Now, this function AY, this AY equal to 1, this thing is valid if and only if Y equals to some Y naught. That's our bulb. If Y is not equal to y naught so the number y, now we are interchangeably talking of y as the name of a person as also a number, but you realize they are the same thing. Yeah, you can replace everything with binaries. The number y runs from 1 to n is supposed to be large, y0 is a number among So you realize this is the classical situation, yes? I mean, this is equivalent to the classical situation. If you only consider this basis, so we are assuming this y basis is orthonormal. They are the names of persons, yes? So when you encode, to be faithful, you must have them as orthogonal. So this is the classical situation. There is one person who will have the same phone number whom Alice wants to find out, and that is the y naught. And then there is something, this ay is written because there could be some complicated machinery that creates the connection between the phone number and the name, yes? It could be some, maybe you are searching on a website or something. So that function that searches it is this a. So it just checks this, finds, but it is 1 only at y naught. At all other places it is 0. Yes, so this is essentially the searching function. And as you see, this is a valid unitary. Yes. It takes an orthonormal basis to another orthonormal basis. Now, this acting once with the unitary U is considered to be equivalent to looking at the telephone directory once. Yes, this is the parallel that we are taking. Finding y0 is considered to be equivalent to finding the boy's name. Question?
the input and gives the name as the output.
Unitary will of course take in vectors only, but there is an encoding mechanism before that encodes the name into that set of orthogonal vectors. That is already done by someone else, and then when it gives out this, and then there is another mechanism that makes a measurement in that basis to find out what is going on. So, as I said, this U is unitary. Indeed, you can check that this U is the identity operator in the Y basis minus twice Y naught Y. Adding everything without the 0 is I. So because you want a minus sign on this side, you subtract twice. And in this formulation, it's easy to understand that it is unitary operator. So our the formulation is complete. Yes, that we formulated the equivalent to the classical looking at the directory thing in the quantum case.
So we have log n number of basis vectors.
Pardon?
We have log n number of basis vectors. Why?
No, n.
Log n bits. Bits.
Yeah, log n.
Qubits.
Log n q.
So U takes input as log n number of lines.
If you want to have qubits. Yeah. So is this where overall. So we will now see what do we get if we in this entire thing we have when we have this formulation, but when we look at the classical end of this the classical way to look at this quantum formulation, we are looking at only this basis. In the quantum case we have other bases, and this is what we will do. And we will see what do we get. As I already told you, we will get a square root advantage. So we will be able to learn the name of the boy within square root of n queries. So this U was, as we already wrote, identity minus twice Y naught. Now set another operator V that is identity minus twice some xi, where xi is the sum of all the y's. So it is all the y's, including the y naught. But we don't know what that y naught is. Take over the entire thing. There's n of them. So it's going to all. we now assume is prepared in the state set. So this is of course a big assumption. In realistic cases, it can be quite difficult to do that because you see these are orthogonal states, so it depends on in what system you encode whether you are able to create such a huge superposition. But this is an assumption that otherwise this thing doesn't work. It certainly in principle can be done. Since we have the y's, we want an entire superposition, it's a typical interference experiment, but a huge interference. The Grover algorithm runs by repeated applications of the unitary these are both unitary, yeah. Check this, easy to check. Just like this I is diagonal in this basis, I is also diagonal in the Fourier basis, and this is an element in that Fourier basis. And it will look, this and this looks exactly the same, but in different bases. It has 1, 1, 1, 1 with a -1 at y naught in this y basis, and this one is 1 everywhere except at this point it is -1 in the Fourier basis. These are both unitary. Multiplying unitaries gives us unitaries, yes. This is a very useful thing. You evolve and then again evolve. The whole thing still is an evolution operator, yes. So this is a necessity. So as we will see, so I will detail it, but the main thing is that what I want to say is that we will repeatedly apply this VU operator.
It's because Fourier transform is a unitary transformation. We are allowed to do this.
Fourier transform is a unitary transformation, but this is not the Fourier transformation. This is a basis, this is a unitary operator that is diagonal in the Fourier basis. Fourier basis is the basis that is obtained from the computational basis via the Fourier unitary that you are talking about.
So when I write VU, I'll use one basis. Either
Of course, of course. You should not mix basis.
Yeah.
If you want to write it as a matrix, use only one basis. You cannot mix basis. But sometimes you can think of them, instead of writing them as matrices, you can think of them as operators. And then you can think about any basis. And then it is sometimes useful. Okay? So we will, instead of doing the general case, we will do first an example. small short. This is only phone. Of course, it's a trivial situation, but it will tell us the main the philosophy. This n is 4, and Alice's beloved, Alice's person is at 2. So this y naught that we were talking about is 2. Xi is half of 1 plus 2 plus 4. U is identity minus this. Which is nothing but 1 1 minus 2 2 plus 3 3 plus 4 4. Which is, and everything else 0. And V is this there is this new car that sounds an alarm whenever somebody goes with a mobile nearby. There's some interference. This value do this a little arithmetic, and you land in minus 1, minus 1, minus 1, minus 1, and 1 everywhere else, okay? So this is hopefully this is correct. And now if you multiply V and U, this also you have to multiply these two. This is still in the same basis, okay? I mean, once we have chosen a basis, we don't change the basis, okay? Otherwise, we cannot multiply matrices. This looks like this, is minus half -1, -1, 1, 1, 1, 1. Check these, huh? Now if you apply this is the operator that we said we will apply again and again. We will apply it on the telephone directory, but the telephone directory is the sum of all the y's, that is the xi. So we will apply it on this xi. So this is this thing and the xi. Xi is 1 everywhere with coefficient half. So this is -1/4, and then you multiply this and you land in this 0, 4, 0, 0. Which is minus y0. Yeah, y0 was the 2. It's not so happy situation all the time. This happens to be an accident that where you do it in such a simple way. Pardon?
How do we know where to stop? We are not doing a measurement during the evaluation.
Yeah, we will see that. Yeah. You will know where to stop. So this is exactly the question that we will ask, that does this happen all the time? Well, we know the answer to this. No, not for a single application of VU. But then the next question is, then in how many, if at all? So as you can guess, with certain number of applications, the thing that is very similar to this happens all the time. Not with a single application, but after some, and this is what we will prove now. Okay. So once more, there are 4 people with phones. Alice wants the person who is at 2. She knows his phone number, but not the name. This person is at 2. Then we consider a situation where the names of the people are encoded as orthogonal states in a Hilbert space. We suppose, this is a big assumption, we suppose that I can create this state from these states, from these encoded states. These are the things that are there classically. I assume that this can be created. Then I also assume that I can build a machine that can implement U. And I also assume that I can implement the V. These are also, in principle, difficult tasks. If this superposition is huge, then this unitary can be a difficult one, so can this V be a difficult one, but we are assuming that these are doable. None of them has any information about the Y naught, in the sense that this, sorry. One second. This V does not have any information about the Y naught. This U, of course, has information about the Y naught. So this is essentially the thing that is given to us as a black box. And so we will compare the classical case of looking at the directory so many times with the how many times we apply the U. So applying U will be equivalent to looking at the directory once. So we will count by the number of times we apply the U.
Yes. So what is the significance of V, sir?
Pardon?
What is the significance of V?
It helps you in the algorithm.
That's
So
also including in the looking part.
but it's considered to be free. Free in the sense, not in the resource sense. Of course, it can require a very large resource to actually implement it, but it is not applying the black box. The black box is the costly resource here. This is an allied resource that you need to run the whole thing. That can also be significant.
So we should always know the Y naught.
In the sense, at the end we want to know Y naught.
Yeah, but initially,
You mean, look, I mean, this you assume that this xi is the thing that you are creating, and this v is the thing that you are creating. You have to check how much resources you need for that. These are allied resources. This is the black box that you are not creating. This is given to you. This is like the directory is given to you.
yeah, that's not the directory. It's a name. It's a labeled directory that we want to find already. The
Exactly.
label
That
already
is true
exists.
for a normal paper directory as well.
No.
That also contains Bob's name.
Yeah, it has a name,
Yes.
but the fact that he is not labeled, it's that she knows the number and she knows where Bob is and she knows the label, the corresponding Y naught.
No, she doesn't.
Then how is she preparing the U?
She is not preparing them. This is the point. It's just like the directory you can buy from the telephone company. This U is given to you by the telephone company, but told that these are the number of times you can implement it. Suppose this is a costly one, it runs only, so in this case, suppose this U can run only once. In the classical case, you would require on average 2 queries. Here with 1 query we are
I
doing.
think the difference is that in classical case, no name is special, in the sense that all directories contain the same information.
Yes.
In this case, given Y naught, you have a corresponding U. In the sense that
Okay.
the operation of the black box is dependent upon that. So
No,
we
you're
can
just
somewhat say that you have some information. You have the number.
The telephone company has that
Yeah.
information.
Yeah.
Okay.
If you
Yeah,
give them
you are
back-
right. You are right.
if you give
So
them
in the
the
classical
number, they
case,
give you the whole directory with
the
this.
classical case, whoever is Alice, the telephone company gives them the same book.
Same book.
Whereas in the quantum case, the telephone
Provide them
company
the number.
provides different unitaries to different Alices.
Yeah.
That is true. Yeah. Thank you. This is the difference. But this difference is not at the user end. It's at the seller end.
आने के time में पता होगा जिसने भी बनाया.
But then this is not a standalone search algorithm. It's not.
Mm,
No, like we are just making a function about the directory, right? Yes, we have a directory. Let's say the directory is not accessible to us, and we are given that directory is with some other person, and
Exactly.
we are asking that person if that number is in the directory or not. We are giving that person a number.
So the
and
number is
asking-
always in the directory. This is the
Yeah.
point. But what his point is that it is true that in the classical case, so the point is that in the classical case, there is some Alice 1 who wants to find Bob 1's number, and there is some other Alice 2 who wants to find Bob 2's number, they are given the same book. Whereas in the quantum case, the seller gives them two unitaries. There's a U1 and a U2 changing with this book.
So my point, I mean, I don't want to sound crude, but the seller could actually say, that person who prepares the box could say where Bob is.
No, that of course is true. But I mean, what I'm trying to say is that this is of course a setup. We will use it for something else. We will not use it to find Alice's beloved's number, this whole algorithm. We will do it for something else. So we are trying to say that there is an algorithm in which you can gain by doing quantum mechanics. This is the only thing. So we assume that the seller will not tell. Because I mean, look, I mean, you can think of that the seller also has to look up at the directory. You can think of the situation where the seller itself is Alice.
Yeah, so then that's my point. That Grover algorithm is not a standalone stats algorithm.
So we are assuming the seller herself is Alice and she already has the U. Yeah, that is true. That is true. So this is the point that this looking at the algorithm, we are thinking of it as this unitary. This looking mechanism, this churning of the directory is being considered as this U operator, which changes from user to user. This is a difference here. This I think.
Is it possible to, by looking at EU, Alice can predict the Bob's identification?
No, not directly.
You mean that, so this is what she is doing actually. So this U has the information about the two. So what she is doing in all this is she is trying to estimate the U. This, if she can look at if she tries to write down the operator for U, she will find out who is Bob. So what she is doing by all this is trying to find out where is this minus sign. So this is essentially a process estimation protocol.
For a given position, say y naught, v is always the same, irrespective of y naught. But for a given position of y naught, u is unique. Right?
Yes, exactly.
So so if y naught is 2, then we have -1 at the second position and so on. So if it is successful this time, why won't it be successful always? Because u is unique for.
Oh, no. So it will be successful. I mean, so if you replace this 2 by 3, this will work. That is not a problem. So by always, all the time, I mean for all n. This is the question. Yeah, if you replace this 2 by 3, this will. That is not. Yeah. What this does not say is if this n is 5, whether or 3, you have to do it again, right? So we will now show that in the general case this works.
We still don't know when to stop though.
Yeah, we will see that, yeah. We will know.
Yeah.
More questions? So actually, in our group, we were talking a lot with this algorithm with several people. I don't know, some of you, I don't know. But so one of the people was Arun Pati, and he has, I think he already put this paper on the web or something. He has a paper on the web on the Grover algorithm, where he gives a variation of this.
Using some ANSI that
He does something to it, and he is able to do it in one step or something like that, which I have some problem with that algorithm. I told him, and he understands, of course, this problem, and or maybe not in one step, in a few steps or something. I forgot the exact thing, but it is done much more efficiently than in this. And there he essentially makes changes with this U and V. And there I was arguing essentially like you, but in a but more, because his thing, he was assuming much more than what has been assumed by Grover. This is my plea, but I have to still understand that better. It's on archive, you can look at that. Okay, so we go on, unless you have other questions. The general problem is actually a very interesting and rather intricate, well, to my knowledge, to my feeling, sort of interesting and intricate exercise in geometry. So we will do the general case now. So first of all, note that this V and U, these two unitaries, are both reflections. What is a reflection? Y and what? So by a reflection, we will mean something like this. So you take two vectors, psi and psi perpendicular. Now in two dimensions, these are unique up to a phase, but in higher dimension, this is not, given this is not unique, yes? But you choose one orthogonal vector. And then, if you choose this point, on this plane, everything can be written like this. Actually, for every vector and another, so this, suppose this is some point and this is some other point. If these two are orthogonal, then is a problem. But if it is not orthogonal, then you can always choose your psi perp so that this thing falls on the plane of this and this. Yes. So you can always write any vector with respect to any other unless they are orthogonal like this. Understand my point? So we are at a vector. This is, you have to think of the points on this, this is somewhat the origin, and this point, and this point are three vectors. Now we choose, so this is the given vector and this is the other given vector. If they are orthogonal, then of course they don't have components to each other. We assume that they are not orthogonal. Then, so you have to think of them as origin, so like this. This, you can think of them like this, yes? Now, given any two vectors, you can always choose a plane that passes through them, and then a vector that is orthogonal to this one, so that this can be written as a superposition of this and this. Yes? This is true in the usual three-dimensional space, but it is also true in these vector spaces and Hilbert spaces. Yes? Now we choose a point here which is minus alpha psi plus beta psi per. Okay. Somewhat similar to reflecting on around this. Yes. Now you choose some u tilde as I minus twice psi psi, some unitary operator and some psi. Then this u tilde, when it acts on alpha psi plus beta psi perp, will give you, so this thing is acting on this. So this is the identity operator. First it will give you alpha psi plus beta psi perp, and then this identity will act on this. It will give you a sorry, what happened? This identity was acting on this through, and then this is acting on this, yes. So, and this will cancel this off, so this will not contribute. So it will be 2 alpha, right? It's minus 2 alpha psi. Thank you. And this is exactly this. Okay. So, you see any unitary that looks like this does this thing. So it is in this sense that this U and V are both of this type. So it is in this sense that U and V are both reflections. Fine. So what? From the proof, this proof, we get an additional information. What? It is that if we start off in a two-dimensional space, spanned by psi and another vector psi perp that is orthogonal to it, u tilde we'll keep it in the same space. Yes. Trivial statement, yes. But we will use this a lot. So, you see the point? The point is that I have a U that is a reflection of this type. That is identity minus twice of something. I take that something, that this psi, and I choose something that is orthogonal to it, and apply it to a vector that is on the plane of these two. The unitary doesn't move it out of this plane. You have to remember the unitary is actually acting on a huge space. We are taking a two-dimensional space out of that huge space. This identity contains much more than the orthogonal than this. This can be 200 dimensions. And this psi and this orthogonal is only 2 dimensions. But this property of this is that this thing that is there, the unitary is defined via identity minus twice of projection of a vector. That vector, and you choose whatever but orthogonal to it. That it is this. And then you begin in this plane, any vector on this plane. Unitary, this u tilde, when acting on that vector, anything on this plane doesn't move it out of the plane. Although there are 198 other dimensions, it doesn't go there. Yes? It went from this to this. Both are in the plane of psi and psi bar. We need this fact. In the Grover algorithm, we start off with xi and apply Vu some s times. Where this V is we haven't defined what is S. We'll come to that. Is an integer. We have said this before, but just to remind you in light of this fact that we are doing this all the time. So the output will in the span of why? Because the two reflections, these two, are with respect to y naught per and xi per where this naught per and xi per to the span of this two. You see this? Because I don't see it.
You can choose these perpendiculars in that span.
Y naught and y per can be y naught per can be written as a linear combination of xi and xi per.
You can choose a perpendicular vector in that span. I think that is clear.
No, thought I understood this.
So xi is 1 plus 2 plus up to n.
Yes.
And then choose xi per as 1 plus 2 plus there's a minus n minus 1 y naught and that sum. Then xi and xi per will span y naught and y naught per.
What is I per?
It's at 1 plus 2 plus 3 plus as it up to somewhere you have to where y naught that the coefficient of y naught will be minus n minus 1.
No, why would that be xi per?
You can choose a xi per yourself.
So that you can write y naught and y naught percent.
No, the interval between xi per and xi should be 0.
output will remain in this
Yeah.
manner.
How
That
would
will be
getting
zero.
1 minus n make it 0?
Because
It should be n by 2 minuses.
n minus 1 minus 2.
एक ही xi per थोड़ी बना सकते
हाँ।
हैं, दूसरा बना सकते हैं।
No, no, 1 minus 2.
y naught और y naught per कोई thing रखना है. और xi naught और xi naught per xi और xi
V,
Y naught और xi
This.
वाले में सब कुछ रखना है।
so this is the U.
xi के बाकी elements में
So I define the
and similarly the reflection से वो
U.
y naught over 2 is
So this is my Y naught,
वो रख दिया।
1. लेकिन वो काम नहीं.
and then there is a xi here.
Initial vector भी
Yes,
xi
so you are applying the V and the U as VU, right? You apply like this. You apply first U and then V, and you are acting it on xi. So first of all, think of U acting on xi. So for the U, this is my vector, and I have to choose a vector that is on the span of these two. I have to choose the y naught perpendicular such that it is in the span of these two. Yes? Because I want to write this as a superposition of this and something else. So then, this being on the span of these two is the same as this being on the, this being on the span of this and this is the same as this being on the span of these two. Yes? It's the same thing. So, this y naught perp has to be on the span of these two. So that takes the xi somewhere, but keeps it in the span of these two. Yes, it keeps it in the span of this and this, which is the same as the span of this and this. So this u xi belongs to the span of xi and y naught. Yes. So now think of this as some chi. And now you apply V on this chi. Now this chi lives on the span of xi and the xi and the y naught. And this V is this. So you have to think of it like this, that, well, you can think of it here. So this is the vector. This chi is somewhere on this space, on this plane. So somewhere here is the chi. And we want to apply the V on that chi. This V is defined via this. So it will be, you want to reflect this about something that is orthogonal to this, on the plane of this and this. So something on the plane of this and this is the same as on the plane of this and this. So this xi orthogonal will also be on the span of this and this, these two. And then you reflect this on this plane. It will remain on the span of xi and xi par, but that is the same as the span of chi, xi and y naught. Should I repeat it? We want to find V, U, xi. And we want to show that this thing remains in the span of y naught and xi. Fine. So let us consider it one by one. First consider this thing. Now when you consider this, you remember this previous discussion that we had, that this is a reflection. It's a reflection with respect to the orthogonal state of this. So what you do is, that is our y naught. And we want to reflect this some xi. First of all, you have to check that these two are not orthogonal. They are not orthogonal. Yes, this has a component, this has a component y. It has all the components, so it has y naught. Now, I want a vector that is on the plane of these two, yes? Because the reflection, what does it do? It reflects this thing in the plane of this and this with respect to a vector that is orthogonal to this. Yes, this is the reflection. So I have to draw a vector that is on the plane of these two but orthogonal to this. And then this u xi is here with respect to this. Yes? This is my y naught par. So y naught par, this was this statement, y naught par is on the span of this. Now we have already got y naught, we have already got u xi that lives on the plane of u and xi and y naught. Now we apply v. This v is again a reflection. It's a reflection with respect to this. So it's the u chi is here. So we have to draw this line and then draw a vector that is on the plane of this and this but orthogonal to this. Yes? Draw it here. We have to draw a vector that is on the plane of xi and u xi but orthogonal to xi. This is our xi par. Now, this vector is on the plane of xi and u xi, but that's the same as the plane of xi and y naught. So the xi par is also on the plane of xi and y naught. This was this. The output will reflect it around this. So it's somewhere there. So this point is my V U Z. Fine. So this was the first geometric fact that we needed. We will do the second one. an exercise in geometry. It's that composition of two reflections, U and V are both reflections. We're talking about those two reflections, but you can think of reflection on a plane with respect to two lines on a plane is a rotation in that plane by an angle that is twice the angle between the lines. This you can explicitly draw and check. So there are two lines about which we are reflecting all the time, and I am claiming that this will exactly be like a rotation, and the angle between the rotation will be twice the angle between the two lines around which we were reflecting. Just draw lines on a plane.
So sir, everything is happening in one plane.
Xi and Y naught. You don't know that plane. Y naught is unknown.
It's a two-dimensional plane, right? We
It's a
apply
two-dim-
V, it stays in the two-dimensional. We apply V, it stays there.
So, just to draw the picture of this entire thing, so you have an Y naught and some Xi. This is how I drew the figure, but you can draw it in any angle, but I will keep to my figure. This is a straight line again. This is my Xi. So now these were the things that are in the unitaries, the reflections, in the definition of these reflections. But to go further, we took two more lines, one that is orthogonal to this. This was the Y naught perp, and one that was orthogonal to this. That was something like this. So this thing is orthogonal and this thing is orthogonal. Let us call this angle as the theta. Then this is pi by 2 minus theta this is again theta and this is again pi by 2 minus theta. Yes. Now the angle pi by 2 minus theta between y naught perpendicular and xi perpendicular, these two lines, this is the angle y naught and xi in the sense that the difference is just phase. This is y naught, this is also y naught. This is only a ray. This angle is also. We want to ask how much is that angle? This y naught xi is 1 over root n. Yes. This xi has all the y's, including the y naught, and each one has this 1 by root n. Setting xi as cos theta this minus is because we are drawing this figure. This phase is not so important. If you look at this figure, it will look like this. We get large n, sin theta and theta are both small, can be considered equal the rotation that we were talking about, rotation of the xi. We reflected xi twice. We said that reflecting twice is like a rotation, and the rotation is exactly by an angle that is twice the angle between the two mirrors. And the angle between the mirrors are the xi and y naught. And because these are rays, is the same as xi and this. And that angle is pi by 2 minus theta.
Mirrors for y not perpendicular and psi perpendicular.
That is true. But you are right. What was the theorem? It's the same thing, because it's up to a phase the same. But in this statement that we wrote here, did we write it about with respect to these vectors or with respect to these vectors? I don't remember that.
The same thing, right?
It's the same thing, yes. But two lines on a plane. Yeah, it's with respect to two lines on a plane. I think we are talking about this and this. Yeah, you're right. So it's just pi by 2 minus theta. So the rotation is by an angle twice of this angle. Is pi minus 2 theta. Which is the same as rotation by 2 theta up to a phase. Yes? Two theta, we had theta is this, so 2 theta is approximately equal to 2 by root n. There's a minus sign, we're ignoring the minus, we are anyway talking about only everything with respect to a phase.
So this will happen when xi and y not part almost same.
The claim is that xi and y naught part y. Yes, yes, xi and y naught part. Yes. That because n is large. So this was one time. But you remember we said we will do S times. There was an S that we completely ignored until now. Come back there. After S rotations, we rotate xi by an angle twice S over root n. We'll add up. So, for S approximately equal to pi root n over 4 rotations. We haven't yet chosen what the S was. We hadn't yet chosen. Now we are choosing it. We choose this S as this. And now don't ask me what is pi rotations, okay? But I mean, this n is large, so
Claim this as an integer.
it's
So
close.
really equal तभी तो लिखा.
So we will choose that n to be large, and then there will be some decimal points that we will ignore. Pi, of course, doesn't end. So for this many rotations, what happens? You put all this. Why did I choose all this? Because this becomes pi by 2. Yes, this is correct. Yes. Now, so what we are doing, we are rotating xi by an angle pi by 2. Which on this plane, which is just the xi part. But then we had assumed this theta is very small. So this is actually y naught.
So can you repeat?
We are rotating xi by an angle pi by 2. So this rotated by pi by 2 will go there, or it can rotate on this side, it's the same thing, it's the phase. It will land on the xi part. You have to remember that we are on the plane of y naught and xi. The xi is in a very big space. There are many other places where it can go to. But these rotations are such that they leave you on xi and on this y naught, the plane. So you rotate it by pi by 2, it will land you in xi part. It's unique up to a phase. But then we assume the theta is very small. So this is actually this. Well, that's the end. We will still discuss a little bit more maybe on the next day.
So but at the end we get somewhere close to y naught. What do we do? We
Measure.
like what measure?
Y basis.
On the y basis.
So we already know the y basis.
Y basis you know.
Number वाला basis है.
That basis you know. You don't know y naught, but you know the y basis.
No, but what does that sort of measure? Just some basically
It's a computation basis based measurement. Yeah, so just like in the Deutsch jobs, we assume that we can in encode the thing in an orthonormal basis, a chosen orthonormal basis, whatever it is, and we can do the measurement in that same basis at the end. We are doing that. In between, we are applying these Fourier terms, Hadamard and so on. Hadamard is essentially a Fourier transformation. So I did not draw the circuit here. That you remember there was a Hadamard in the Deutsch-Johnson. Here that is creating this xi. So we stop here. We continue next day with this.